Fundamentally, I don't believe in sovereign anything, to be
Okay,
absolutely honest.
sure.
But I think clearly it makes sense for countries to have a strong ecosystem that is resilient to overall geopolitical changes. So from that perspective, I think it's not so much about a data center versus an edge, but it's really about a healthy supply chain that can work uh, across the overall cyclical changes that semiconductor industry goes through.
Welcome to another episode of AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. In this episode, I'm sitting down with Sakya Dasgupta, CEO of EdgeCortix, to talk about the company's reconfigurable dataflow architecture, as well as their success with NASA and space applications, and why Japan's the right place for a semiconductor company in 2026. I also got some sneak peeks at what's coming up in EdgeCortix's third generation hardware architecture, which will launch pretty soon. Here's my conversation with Sakya. Okay, hello Sakya, and welcome to the show.
Hi, Sally. Thanks for having me.
So for EdgeCortix, you're an Edge AI chip company, and you have more than one generation of product out in the market. So EdgeCortix has been around for a little while, but maybe you could kick off by telling us a little bit about, how you started EdgeCortix, how the company began, and what are the origins of this idea?
Sure, absolutely. Just to kind of kickstart things, I would say the best way to classify us would not necessarily be an edge AI company per se, but I'll say we are an AI inference focused company where fundamentally the reason we exist is to make AI processing a lot more energy efficient, faster. So a lot of the applications we are targeting is real time. So latency is a critical component of overall kind of the architecture focus for us more than throughput per se. And then effectively, the way we measure efficiency is performance per dollar and performance per watt. So both cost efficiency as well as power efficiency are critical metric that we try to optimize for end customers. And rather than focus purely on the chip, from the very beginning, our focus has been the duality between software and hardware. In fact, if I recall correctly, in 2019, when we started, we were among some of the first few folks who started using the word software first. We are very glad that it's terminology that is now pretty mainstream in the industry. But the idea was tackling software and the compiler stack, targeting the broader edge market, which is dominated by constraints of power, size, weight, at least as the first target area that we could focus on, and then build silicon together with that software that helps deliver on those promises and metrics.
So the gap in the market that you were looking at in 2019 was latency and power efficiency, or some combination of those, right?
Great question. So I would say more than the metric per se, when we started in 2019, fundamentally we found that there were a number of companies that were already looking at silicon for AI hardware. A lot of that was dominated on the data center at that time, not much on the edge. And the companies that did focus on the edge still had that hardware first mindset. Hardly anybody was talking about software and the solution aspect of it. I'll give you an example. Like, for example, I come from 20 years in the AI industry. A lot of that experience has been on the software side. And the critical challenge we face when we are deploying a solution for the end customer is not how much TOPS a chip has, but can it really run the frontier model that I want to run? Can it give me the frames per second that I need? And can it do that at the required amount of power consumption? That's really the problem setting that we started off with. Like, how do we deliver something that's going to be solution centric rather than a spec of a hardware chip, and then essentially come downstream from there and design the software and the hardware targeting the broader edge market?
I mean, even with a brilliant idea, commercializing brilliant ideas can be really tough, especially in deep tech, where we are. What would you say was the most difficult thing you've come up against when kind of commercializing this idea?
I mean, in general, I think as a deep tech company, we face the same challenges as any other. Fundamentally, when we start a deep tech company, in our case, that's the same situation. We start with a vision and a conviction from an engineering standpoint that we in a manner, believe in that overall architecture and kind of the value proposition that we'll bring to the table. But the fundamental challenge is how do you go from that engineering specification and design to a solution that a customer is willing to buy? And then how do you 10x from there? So, for example, getting to the first $1 million revenue and getting 10xing from there, that's the fundamental challenge. And in hindsight, in the last few years, we've been able to do that. And I think that's been the main proof point for us to go from a concept as a deep tech company, building an MVP product that meets those points, getting the first customer who's willing to essentially believe in the idea and put it to test in their production systems, and then 10xing it from there. And we've seen that journey and growing our overall customer base. And I think that's really in a manner, we are still growing as a young company, but I would say we have come full circle in our deep tech journey, where I would not call us purely a deep tech startup anymore, given that we are already in design with many of our customers today, proving the architectural elements in actual solutions which are being deployed.
All right, let's talk a bit about the product. Sakura 2, this is your second gen chip. You launched in 2024, so it's been out in the market for a little while. This is 60 TOPS in 8. There's DRAM on the card. You have single and dual chip cards. I want to talk about the NPU. I think people who listen to this are going to be interested in exactly what's going on in this NPU. DNA, you call it Dynamic Neural Accelerator. Tell us a little bit about DNA and how you distinguish your kind of data flow and data path, your version of data flow from other people's.
Sure. So great question. So before I get into the DNA aspect, let me kind of, using the same context of the question, touch upon the previous question as well. When we started in 2019, a lot of the world was focused on vision processing. As a result, our first chip, we call it Sakura 1 at that time, which uses the early version of a DNA architecture, was pretty much vision centric. So we optimized a lot for models which are convolution type of operations, and we did not focus on mixed precision as much. We really focused on integer bit precision, as a lot can be done with those types of models. Today, where we are, effectively maybe a couple of years into our journey, we realized that the industry was steadily shifting towards transformers as a model that is a lot more memory centric rather than compute centric, or rather memory bound than compute bound. That has gone into our architectural modifications very early on. So DNA as it stands today is still a data flow architecture, but fundamentally we designed it to ensure that we can minimize our communications required with any external memory as much as possible, and overlap the compute to be as much localized as possible within the chip. That enables us to essentially uh, maximize the overall performance of the chip without sacrificing power and latency, which would be the byproducts the moment you go off chip. So that's been one big building block element in our design in the last few years. Second, the data flow architecture also kind of embodies some degree of flexibility. So where the name dynamic comes from is that in our first generation itself, we had invented you can think of this as a highway or a bus that connects all the compute elements across our uh, array, whether that's our matrix engine or vector engine. We have both. And that compute bus can be dynamically controlled uh, at runtime to essentially either run all the compute elements in lockstep, where all of them work together as a synchronous unit, or we can effectively disconnect or decouple some of those compute elements. This enables us to trade off the compute requirement vis-a-vis the power consumption and the performance that we would get. Or in other words, effectively optimize utilization of our compute elements. That's what gives us much better effective performance per watt. So we are essentially either reducing the denominator, which is power. Of course, the roofline number of tops never really changes. But the objective in our design has always been, how do we get closer to that roofline number as much as possible? As you would be familiar in your audience, that most of the numbers when people talk about tops is really a roofline number. And very rarely, if at all, you would reach 100% of that. And that's been one of our design elements, that the dynamic element comes from this compute bus that connects all those compute elements, and then we are able to maximize our overall utilization, get as close as possible to that 100% in a workload-dependent manner. And then mixed precision and all those elements kick in to support what you require today with transformer models.
I'm very curious about this runtime reconfigurable or reconfigurability. It seems like it's the connections between the compute elements that are reconfigurable. Is so runtime? I mean, does this mean compile time, or is it? I know it reconfigures during the course of one inference, but that reconfigurability is decided at compile time, right?
Correct. We are still statically compiled, but at runtime, we can stitch those compute elements together where we can decouple some of those elements. So we are still creating. So fundamentally, we again believe that in order to optimize latency, it's better to statically compile because you have the access to the overall graph information. So we don't do what GPUs may do. So many GPUs actually have dynamic compilation. We don't do that. So we are statically compiled, which also ensures that we are deterministic in terms of our execution. We do not introduce stochasticity, but now we can effectively turn off some of those elements. We cannot add new elements into the picture, but we can decide which of those compute blocks can be switched off even in a layer dependent manner. So for example, let's say you are working on a large multi-layer neural network, and if each of the layers do not require all those compute blocks, then I can effectively turn off some of those parts. Equivalently, the same runtime reconfiguration nomenclature is also used for mixed precision. So some layers can run at a higher precision, some layers can run at a lower precision. This again helps us to trade off accuracy versus speed, which we have found to be very effective in some of the latest large language models or language vision models that we are able to run on Sakya 2.
When
But
you
I would say that our
say,
next
sorry,
generation, and I would say that in our next generation, we are going well beyond that, but maybe I can talk about that a little bit later.
for sure. Um, so when you say mixed precision, it's BF16 and int8 today, I think. I'm curious about what kind of workloads, you kind of touched on it a second ago, what kind of workloads need that BF16 precision today? Because I think the trend for LLM certainly is to move to lower precision for inference.
Yeah.
And I'm curious also, would you support fine tuning or something like that with a floating point that you have?
Yes, great questions. So three things that we are effectively enabling customers to do to make the workloads a lot more robust. While at the hardware level, we support BF16 as well as integer rate, we can do 4-bit approximation. It is possible
Okay.
for us. So it is possible for us to have some amount of workloads that can run at the 4-bit level with approximation. At the hardware level, it is dedicated integer rate support we have. So you can run everything in integer rate, or you can run everything in 16-bit, or you can run in mixed precision mode up to 4-bit level. We do see actually there are applications that we are running. In fact, very often the large language models that we run, especially even SLMs, we are seeing that many of our customers choose to run at the BF16 level because we are actually hitting much more higher accuracy. And in our case, with 30 teraflops of dedicated BF16 that is available at dense level without any sparsity, that enables us to run pretty large workloads. So we can hit more than 20 tokens per second, even at BF16 mode, with some of the largest models out there, up to 8 billion parameter Llama model, for example, version 3. So we have seen customers actually choosing to use those BF16 models. The integer models effectively come into play when there is a space or a particular power constraint required by the customers. In the next generation, by the way, we today already have a 3rd-generation DNA, which is going into our chiplet architecture. There, we in fact have, and a little bit early to talk about it, but since you asked the question, we have support for even floating point 4-bit, including supports that we are seeing today standardized in the industry. So for example, I think today, even in the data center side for inference, we are seeing formats like MXFP4 or NVFP4. There's slight differences in the exponent and the mantissa, but the way we have designed our next generation IP is that we have support for essentially flexibility from 16-bit floating point all the way to 4-bit floating point as well as integer precision. So I think your other point was regarding uh,
Fine
I'm
tuning.
losing the
Yeah.
fine tuning. Yes. So
Yeah.
fine tuning is absolutely possible with Sakura 2. In Sakura 2, the way fine tuning would be possible would be to use something like low rank adaptation LoRa. So LoRa is possible from a software standpoint. We, while we have floating point, we cannot in Sakura 2 support gradient updates. So if you have gradients that you would want to change directly on the chip, we do not enable that today for our customers. But low rank adaptation can be done. That enables us to effectively fine tune a part of the model. Um, uh, and yeah, so I think that's kind of the level of support that we have with Sakura 2. In our next generation, again, um, we have, because of the flexibility that we have added, uh, we are also tending towards what one would call programmability. So fundamentally, I believe that today the industry is dominated by transformer models. I've been in the AI industry in 2 decades now, and clearly, um, models and hardware kind of scale in a manner that typically software scales much more faster, at least from a model landscape perspective. And I do not fundamentally believe that today's transformer models, as it stands, will remain exactly the same 5 years from now. As a result, if you are building some hardware, we got to have some degree of flexibility built into it. And we are already seeing many of the customers, especially in physical AI, robotics, wanting to have some degree of flexibility to even fine tune parameters at the edge level. I will just say that we are preparing towards that eventuality with our next generation IP.
Understood. Thank you. Going back to kind of the current gen Sakura 2,
Sure.
new for this generation, you had this dynamic reshaper engine, which was very interesting to me. Tell us about this reshaper. What is it, and why do we need it, basically?
Okay, the reason we need the reshaper engine, which sits alongside our overall, let's call it NPU, is effectively to manage large tensor manipulation operations. So we found that whether that's convolutions or even transformers, many a times we have to deal with large tensors that may require to be flattening them or stretching them. Essentially, you are reshaping these tensors, which can be pretty heavy operation if you have to go off chip to a CPU. As a result, we added dedicated IP on our chip itself so that, again, going back to that original concept of minimizing off-chip communication, which is expensive from latency and power perspective.
So let's talk about Mera a little bit.
Sure.
This is your compiler. I understand you're a software-first company, so Mera in its first form was developed first. How complicated is it to make a compiler for something that is reconfigurable like this? The compiler's doing a lot of heavy lifting here, right?
In general, I think the compiler has to do a heavy lifting for almost any kind of hardware. And
Sure. Okay.
and I would argue that really the compiler is the elephant in the room that many a times does not get talked about enough. So when we really started with that compiler journey, knowing very well that um, AI, if you're designing anything for AI, it's essentially graph. And for that graph of operations, you got to think from a software perspective how to ensure that the user experience with what they're accustomed to, let's say a GPU-centric computation, gets preserved from a software standpoint. And then you build in all the instruction set architecture level, ISA level efficiencies that the compiler can then talk to at the low level. The way we tackled this problem was to essentially build a compiler while the uh, architecture was built together. We actually use, one of the companies to be early adopters of Chisel as well. So we started essentially with a programming-centric language. As you're aware, Chisel is a very much Scala-centric language that is really designed very well to go with a software, hardware co-design principle. So we designed those in a manner at the same time. Um, and then at the compiler level, the objective really was if the edge market is very fragmented, where you have many different types of heterogeneous hardware that exists at a system level. So, for example, in a data center, if I'm deploying a solution, typically the system hardware may not change as much going from one application to another. All applications run on the same type of, let's say, data center system. In the edge, that's absolutely not true. A robot may be sitting with an ARM processor already today with some cameras, LiDARs, or radars. You might have an industrial vision application, which are cameras running on an x86 compute box. And now we also have RISC-V systems. By definition, any software that runs on an edge system needs to talk to multiple different hardware. That was another design principle. So the way we deal with this is we understand our own instruction set architecture very well, but we also understand LLVM very well. That enables us to work with x86. We understand ARM's Vela compiler very well. So if required, if you're working at a system level which ARM is combined with our processor, we can offload parts of that to ARM's Vela compiler. We don't have to reinvent the wheel there. And same thing we are now doing for RISC-V that we are able to add to our next generation processor. So that's another design element that the compiler at a high level is able to tackle. And then when we go one level above, we also added support for things like an interface with Hugging Face so that we don't have to reinvent the wheel to do all the pre-processing and post-processing ourselves. There is a standardization in the industry today with thousands of models that already work on Hugging Face. We can bring those models directly on our platform. And then we also became one of the early adopters of enabling multi-platform compilation. I think today almost everybody is compelled to support PyTorch, TensorFlow, NNX. We started with that from the very beginning. So I think Cafe existed in the past, it no longer does. So we have gone through that exploration ourselves. But today we support PyTorch, we support TensorFlow, TensorFlow Lite, ONNX. We don't force customers to quantize with our tools. If a customer wants to run a model which is pre-quantized on PyTorch or TensorFlow Lite, they can choose to do that. So those are some of the building blocks aspects, again, solution-centric thinking that I think we started with early on. That has really shaped our compiler journey. And in a manner, as a result, our compiler is pretty much a standalone product alongside our overall hardware.
Yeah, I mean, I understand why you'd want to compile to your accelerator and an ARM CPU, say, but beyond that, could I apply Mirror with other types of hardware, or how hardware agnostic are you?
Great question, right? So, for example, the whole idea of a heterogeneous compilation compiler goes well beyond just our ISA. As a case in point, historically, we have also licensed our technology to other companies. At least in the public domain, you would have heard of Renesas Electronics leveraging our Mera compiler solutions, kind of the entire software stack. Every microcontroller and microprocessor that Renesas makes today, at least in the public domain, we have talked about the RZ and the RA series. Uh, these, by definition, are heterogeneous. They have,
Yeah.
as an example, RZ series has ARM cores. It may have an NPU, which could be somebody else's or Renaissance's, and you might have an ARM NPU as well. That's a heterogeneous by definition. So Mera can manage that workload. So where it does not understand the instruction set architecture very well, it will then only be able to provide higher levels of features, which may be high level graph optimization. It may not be able to give you low level kernel optimization because we do not have, let's say, the ISA understanding. When we have the ISA understanding, then you unlock the full breadth of all the features of Mera. That's the only difference. So the question is at what level you cut the
Yeah.
overall software efficacy.
If someone's listening to this and they like the sound of Mirror, do you still license that to other companies?
Where we are today in our journey, we realized from the very beginning that we were building Mera for an eventual heterogeneity that will happen across the hardware stack. The heterogeneity exists at the market level, which I talked about already, edge. At the semiconductor processor level, that heterogeneity is really chiplets, in our opinion. And that's why our roadmap also naturally today is on chiplets. And Mera really is designed to fully provide that efficiency for chiplets that we are building, which are heterogeneous by definition. So I would say today Mera is pretty much an integral part of our own roadmap. We are not looking at uh, licensing Mera exclusively for many customers, but we take a selective outlook towards it. When it makes strategic sense, that could be an overall strategic value add, even for our hardware or DNA IP, for example, that's where it makes sense for us to provide access to overall mirror. What we
Yeah,
are really concentrating today on, and where we are really seeing our business grow, is on our chip side with Sakura 2. We already have many design wins on Sakura 2 chips as well as on modules, M.2 PCI cards. And we are also now focusing on our next generation chiplet platform, where Mera will essentially become the key enabler.
absolutely. One of the things you mentioned a couple of minutes ago that sound really exciting is this programmability to the point of supporting kind of arbitrary operations, or let's say user-defined operations. Are we talking about supporting in software or actual hardware acceleration for these arbitrary operators? And how do you achieve this?
Yeah. Yeah, multiple levels. So, as an example, in Sakura 2, we already support some degree of programmability. For example, we support arbitrary approximation of activation functions.
Yeah.
And we have seen that activation functions has changed quite a lot in the industry. And as a result, we did not want to necessarily have all types of activation functions implemented at the hardware level without, which one way of doing it is having a completely programmable ALU, but which is, of course, a trade-off of complexity, power, area. And the other way is having some degree of flexibility at the software level where you can approximate certain types of activation functions with piecewise linear kind of types of them. We support that already at Sakura 2. With the next generation, because the chiplet platform is very much scalable, you can add significantly more performance. We are adding both hardware level of programmability as well as software level. Software level I've already described, which is really coming from Mirror. Hardware level would mean that microcode level programming. Today you have that already, even with GPUs, I would say. So CUDA is very well known in the industry, but alongside CUDA, there is also another compiler that exists, as we know, that enables much more lower level microcode programming as well, even in case of GPUs, or at least some types of GPUs in the market. Our next generation is designed in a manner that we have both that hardware level of flexibility to a certain extent, without going all the way down to an FPGA level of flexibility, which would be, you know, making it a lot less efficient. So we are still an ASIC in that definition, but preserve programmability to a certain extent that building blocks, which we don't expect to change, like the building blocks of, let's say, a neural network, can be composed together to create arbitrary operations, and also supporting even things like DSP type programming. So, for example, things that could be just pure mathematical function. Many chips today in the market struggle to implement operations like tanh, or even things like a sigmoid, or an exponential function, or a logarithmic function. So we solved some of those problems in our next generation.
That is pretty exciting. Okay, let's change tack a little bit, and I want to ask you about Japan, because I know your HQ is in Japan. I know you identify as a Japanese company, even though you have a global presence. Tell me about why Japan is the right place for a fabless chip company in 2026.
I think if that question was asked differently, why Japan is a fabulous, kind of
Yeah.
successful place for a fabulous company in 2019, 2020, the answer would have been very skeptical.
Okay.
Today, there is really no better place, to be honest. If you look at the overall kind of tailwinds, since we started in 2019, there has been a resurgence, so to speak, of the overall semiconductor ecosystem in Japan, where there is a steady influx of both government support, which goes a long way for many deep tech companies. Uh, in our case, we have been generating revenue from an early stage, but that may not be the case for many other deep tech companies. So today, Japan is providing that benefit for deep tech companies to essentially have non-dilutive capital accessible. That makes us a very apt environment to build fabless semiconductor company like us. Second, there is also a lack of fabless semiconductor companies. And I always argue that if you're building a company, it's a good idea to be in a market where your overall demand vastly outstrips supply. And we are in that environment. So we are absolutely building a global company, which is reflective in our overall team compositions. If you look at even our leadership team, which pretty much reflects our engineering team as well, very global. We operate pretty much as a Silicon Valley style company, if I may use that nomenclature. English is the common language, but we are building a global company out of Japan, where Japan provides us that apt environment to attract talent, good access to non-dilutive capital, a strong environment where we can have global talent available both locally as well as internationally, and then a vast amount of demand that we are seeing both for AI as well as semiconductor tech, and we are pretty much in a very unique position today in that market.
How much of your business or how much of your customer traction would you say is in Japan today?
40%. Overall, our overall pipeline, I would say 40% is on Japan, 60% is non-Japan, and the largest non-Japan portion would be North America. So that is already reflective that we are, out of hundreds of customers of the overall pipeline that we are serving today, 40% is Japan, 60% is still pretty much global. So I think we are still, catering to the global audience. But nevertheless, in Japan, we are seeing a good concentration of industrial, robotics, some aerospace customers as well.
I'm curious about, to what extent do you think countries need like a sovereign AI chip play at the edge? We're very familiar with this in the cloud space. People want to build, governments and countries want to build big AI data centers that they can use for their sovereign projects. But do we need that at the edge too? Do we need a sovereign edge AI play?
Fundamentally, I don't believe in sovereign anything, to be
Okay,
absolutely honest.
sure.
But I think clearly it makes sense for countries to have a strong ecosystem that is resilient to overall geopolitical changes. So from that perspective, I think it's not so much about a data center versus an edge, but it's really about a healthy supply chain that can work uh, across the overall cyclical changes that semiconductor industry goes through.
Yeah.
And that's the reason in the very beginning I mentioned we don't see ourselves per se as an edge AI company, but really targeting AI inference to be much more efficient and really building AI inference infrastructure to be efficient with a software and hardware combination. And from that perspective, I think the edge and the data center are pretty common in terms of what is required for countries to have their own capabilities. While at the same time, I think even in Japan today, we are a very good example of, I would say, a trans-Pacific collaboration scenario where we are in Japan. We, of course, have presence in the US. We have design team and even in India. We design our chips in Japan. We are producing them today in Taiwan. We are selling it in US, Japan, Europe as well.
Yeah. Yeah. Okay, I think one of the most interesting applications that you're going into already is space. The nerd in me is very interested in AI and space for whatever reason. I understand you've been working with NASA to test Sakura 2 for suitability, basically for going into space. I mean, this is a product that wasn't designed to be rad hard, if I'm correct. Like, how did you end up with working with NASA and doing space testing?
Yeah, it's very interesting. So much like most things in life, it's serendipitous.
Yep.
And for us, you're absolutely right that we did not design for space, but we definitely designed for robustness. When we started as a company, we did look at automotive as a market, but quickly realized that it was a market which was crowded as well as it required a lot of certifications, which we did not want to take on as a company early on. So we did not focus on automotive, but we focused on everything else in the market. But from a design perspective, we did design with certain amount of robustness that is required both at the RTL level as well as at the software level to maintain resiliencies. Later on, we discovered that NASA, much like most other efforts in the industry, was looking at commercially off-the-shelf devices or COTS devices to work in the space environment, fundamentally because of two reasons. One is cost efficiency, the second, or design cost efficiency, and the second is really not having to invent the entire software stack. As we know, the entire software stack today works on COTS, commercial platforms, not really for space gate platforms, which are typically 5, 6, sometimes 10 years older. than what the current gen technologies in commercial side. And that resonated very well with our devices. So NASA actually approached us to test a particular program from NASA called NEP, NASA Engineering Parts and Packaging, which effectively took on the task of testing our devices for robustness in space environment. We call it rad tolerant rather than rad hard because we are
Okay.
not doing any special packaging. So the same chip that works in a commercial environment without any packaging changes is being tested for extreme radiation cases across LEO, GEO, as well as lunar environment. And going through that process, we discovered that not only Sakura won, which came out with flying colors, just to give you a number, NASA was able to validate that we were 10 times higher radiation tolerant as a COTS product, even when compared to some non-COTS category product. We repeated that process with Sakura 2, and there was virtually no difference in the results. As a result, today, our Sakura 2 products, which is the main production products today, is fully qualified for essentially environments which have uh, up to pretty high 46, 47, maybe up to 50 rad, exact numbers I'm forgetting, but this is public information. But what it effectively boils down to is it enables us to operate in LEO, GEO, as well as lunar environments without uh, essentially witnessing even a single event failure during any of those trials that NASA went through. And we are now partnering with companies who are operating in the space environment, from satellites to lunar mission companies.
Um, what are the potential space applications? I mean, we talk about LEO, GEO, and lunar here, so it's satellites and so on. But what kind of AI do they want to do in space with 60 tops?
So of course we will not stop at 60 tops. Again,
Okay.
much like everything in our roadmap, our next generation, which, as I said, it really scales up in performance. We expect the same uh, results that we have witnessed with our current generation to even be true for our next generation. Today, immediately with Sakura 2, in the satellite side, we are seeing application where they are effectively looking to run localized, relatively low power AI inference on board the satellite. Uh, Things as simple as just cloud detection. We would not imagine that a lot of the computation actually goes in detecting which is the cloud and which is not. The standard segmentation algorithms being run without requiring any kind of other special kind of tools. An application that we are looking at which is in the public domain, we have kind of mentioned this together with a company called iSpace, who is a lunar mission company. There could be applications in a lunar lander, lunar rover, which effectively increases the efficiency of both the landing system and the rover. In fact, in CAS this year or earlier this year, we demonstrated together with iSpace a prototype platform of the lander and the rover, and we showcased on Sakura 2 platform, which was effectively running with a small uh, powered system as a Raspberry Pi combination on the rover as well as on the lander, where the rover can then use its cameras to operate, detecting this terrain, running, for example, segmentation models or other types of object detection models together. So multi-model running on a single chip, and then effectively communicating with the lander, which will have much more heavier compute capability. So yeah, these are applications which we are seeing realized as early as next year.
This is so cool. I think lately we've seen CEOs of some big companies. I'm talking about people like Elon Musk, Jensen Huang, talking about building AI data centers in space. And one of the things that comes up time and time again, one of the biggest issues people like to point out is how do you dissipate heat from compute in space? How do you do this for Sakura? Or how do you propose to get around that with Sakura 2 if it's in a satellite? How do you get rid of heat?
Yeah, no, that's a great question. So the question, see, a data center is, of course, requires a very different amount of heat dissipation. So it's absolutely a very different physics problem, and I think it
Yeah.
needs to be addressed before we start building data centers. But on a satellite, if you're dissipating essentially 3 watts of power, it's not something that is not already happening today on those satellites.
Okay.
So it's a very different problem. So yeah, I mean, we are aware of orbital data centers. We are looking at those opportunities, but immediately where we are seeing the realization of our Sakura 2 chips in space applications are satellites and rovers uh, and landing systems that typically require few watts of power consumption from our compute device, not
Yeah,
thousands of watts of power consumption or even higher that a data center would require.
got it. Um, okay, I know you have customers in aerospace too. Can you tell us anything about what their applications look like? How are they using Sakura 2?
Sure. So from the very beginning as a company, we have embraced applications that could be dual usage, wherein the same type of application that we see in an industrial or a robotic setting is being realized in for example, UAV or essentially an aerospace system, where communications and AI processing may go hand in hand. So today we work with few different companies. So we have design wins with multiple aerospace companies, both in Japan as well as in the US. Um, while exact applications, I will not be able to elaborate deeply, but typically we are seeing applications, for example, in carrier aircrafts requiring um, uh, AI inference capabilities on board that needs, again, low latency, the ability to run multimodal transformer models, which we were also quite excited to hear and see those being realized. And we have gone through companies successfully flight testing this in early days, where now, together with Defense Innovation Unit, with whom we became the first Japanese company actually to win a contract with them, we are seeing that realized in actual applications across. The direct customer would be a U.S. government entity.
Yeah,
Similarly, in Japan, we are seeing applications with Japanese aerospace primes, which again require uh, application that can span from detecting uh, images or videos that could be at lower resolution and then increasing the resolution to be able to understand the scene better, but you need to do this on the fly at low latency, and then being able to run on the same system additional operations that enables you to understand that image. So scene understanding, for example, needs to also happen alongside any kind of resolution changes. So at a high level, those would be application examples where we are seeing those being realized by our customers on our platform. Many cases, customers also choose to combine our chips with even other forms of processors, which are more prevalent in the industry.
yeah, yeah. Um, okay, so I know you're also working with the AI RAN Alliance. I know you already spoke to E times about that, and I'll put the link to the video where you speak to Nitin about the AI RAN Alliance. I'll put that on the podcast landing page so people can read that or can watch that if they want. But the AI RAN Alliance, I mean, this is for telecoms infrastructure, completely different application to the space and aerospace that we're just talking about. This is a completely different workload. Am I correct?
Yes, that is correct. However, I would not say it's a completely different workload, but it's differently aligned to where we are today. For
Okay.
us, the overall AI RAN industry is not near term. It's really a much more longer term journey. And we expect the telecom industry to essentially shape up in that direction, where historically, I would say the promise of 5G, so to speak, was not really delivered at the highest level that we expected in a manner because I think AI was at a different stage. Today, what the AI RAN Alliance is trying to do is effectively bring an again dual usage in a different sense where the single infrastructure, whether that's a system or a chip, could be used not only for AI processing but also be used for parts of radio access network processing. In 2023, together with SoftBank Corporation, this is again public information, so I can talk about it. We demonstrated that our IP, when applied to parts of radio access network processing, which is very close to the physical layer, we call this layer one. This is very heavy on mathematical operations. Almost 48% or 49% of the compute is math heavy. Forward error correction, modulation, demodulation, parity checking. These are typically the operations that happen there. We are very good at doing these in our ISA. And we demonstrated at that time that our IP, when even compared with another IP, which is much more common in the industry, uh, when implemented on an FPGA, was able to achieve very high throughput and performance while also achieving higher accuracy. from a BER, a bit error rate perspective. That went into our own architecture and design. So what we're expecting in the future, again, a couple of years down the road, uh, our chips and systems will enable not only AI inference processing at low power on edge and let's say the thick edge component, where you're able to scale up to uh, even thousands of tops of processing, but the same chip and system without any changes will be able to also do uh, bulk of the distributed unit layer one closer to the 5 layer processing, which is typically again a bottleneck. So yeah, so that's kind of the overall vision, and that's our role from an AI RAN perspective. We call this AI with RAN, where AI and RAN can happen at the same time. But again, it's not a very near-term objective for us. It's a little bit more longer term, and but we expect the overall market to mature in that direction.
Okay, I got it. Beyond space, aerospace, telecoms, I mean, do you work with customers just in the ordinary industrial arena, like smart
Yes.
factory type? Yep.
Where do we make money, right? So where
Yep.
we are making money is really in industrial. So that's a pretty large segment of our overall customer base and design wins today. We also have customers who have taken our chips and build their own hardware platforms, which have even gone into environments like enterprise servers. So in that sense, the edge in a manner has expanded, so to speak. But this is really being deployed for things like a smart building, let's say a smart infrastructure. If you're managing, let's say, a factory floor or an entire building with AI inference compute, in that case, this particular customer of ours takes our chips, builds their own hardware that goes into even rack mounted servers. And we are able to provide much better performance per watt efficiency compared to, pure GPU reliance. So we can co-locate with the GPU when required. Robotics is another good application area where we are seeing design wins already. And applications include, in the beginning at least, social robot platforms, so semi-humanoid, let me call that, where you have a wheel component, but you might have a robot that needs to interact in a physical world. As a result, it has cameras, it has other sensors, but then it's really communicating with a human. And in that case, they've been able to use uh, models like Whisper for speech to text, text to speech, and then large language model or a small language model at the back end that essentially provides you an interface. And you may also have a RAG component that is tapping into a localized knowledge base, which is really tailored to that particular customer.
Yep.
Aerospace and space or dual use application, that's another area we've already seen good success today. Yeah, so these are,
Yep.
I would say, really what covers the bulk of our revenue and where we expect the market to grow.
All right. Let's talk a little bit about what's next on the roadmap with Sakura X. I mean, we've been pretty heavily kind of trailering this all the way all the way through, which is really exciting. But so for Sakura X, this is going to be a new generation of NPU. This is going to be a bigger chiplet-based design. Is that what you've got in mind?
Yeah. So yes, all of the above. So
Okay.
fundamentally, with Sakura X, we are really embracing chiplets, and we've been talking about this for some time now. In fact, over the last I would say almost 3 years, we have been talking about the overall chiplet ecosystem. And rather than bet on dies, we are really betting on homogeneous platforms first. So we are building the chiplets so that each of the dies can talk to each other and can be a standalone product. But of course, each of the dies can be used separately. And we have not only enhanced our NPU as we have been discussing with elements that make it future proof towards the eventual transition that might happen beyond transformers. We have also been able to upscale the memory, which we fundamentally see as the major bottleneck. So we have industry leading memory bandwidth. We have industry leading in today's generation, best in class SerDes as well available that really within, again, the tens of watts of power consumption still provides us a very high performance per watt. Both whether you look at tops per watt numbers or even actual uh, usable tops per watt numbers. Beyond that, for us, really the bet is that I think chiplets are here to stay, and we are really betting on overall heterogeneity and system scaling aspects of semiconductors. So we today also own the UCI technology ourselves. And that enables us to ensure that we not only have our own NPU, we have our own chiplet roadmap, but we also own the UCI technology to enable that we can talk to somebody else effectively as chiplets become heterogeneous, truly in that sense, in the future.
All right. When do we expect to launch Sakura X? Is it 2026 or further down the line?
Fairly soon, I would say. We
Fairly
will
soon.
have we will have a lot more news to share. But yeah, we are pretty much on a very much accelerated roadmap. And I think it is much more sooner than people would think.
Thank you, Sakya, for the illuminated conversation. If you want to learn more about EdgeCortix, check the links on the podcast page at etimes.com. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. AI with Sally is brought to you by Aspen Core Media. Thank you for listening.